figure, right? It went from, like, if we had a triangle of ABC, when I flip it, it's now gonna be a CB, and the order of the letters is gonna be different. When I do a rotation, it's still gonna be RSTU around here, but what we're doing is we're taking the figure and we're sitting it in a little bit different way. And so we're gonna rotate it 90 degrees, 180 degrees, a lot of different ways. I'm not gonna go through all the different rotations since we're not gonna spend a lot of time with this. I'm not gonna spend the time talking about it, but just know that a rotation is taking the entire figure and rotating it about the origin. And you can kind of see the arrow here. For a rotation of, if I go into the second quadrant, like let's say I took R and rotated it into the second quadrant, that would be a 90-degree rotation. If I rotate it into this here, that would be another 90 degrees, which would then be basically 180 because it makes a line, right? Then I could come over here, that would be another 90. And if I come back to where I started, oops. If I come back to where I started, I've moved a full 360 degrees. So if I do 4 90-degree rotations, I'm right back where I started, right? 360, which makes a circle. But you could break it up into different increments. You could break it up into 4 different rotations, a 90, a 180, a 270, and then a 360. So we're just adding 90 each time. So sometimes, eventually, like, we won't talk about rotation as much here, but if you ever get into a little bit more in depth in geometry, that would be one topic that you might see. Excuse me. Really what we want to know here, do these figures have rotational symmetry? So for instance here, can I rotate this figure? Will it map onto itself? Okay, so it may not be a reflection. Okay, we already said like a figure like a parallelogram doesn't have a line of symmetry. So there is no reflection that's happening there. What about a rotation? Well, like for instance, this point here, I can move it a full 180 on the clear on the opposite side, and that would be a 180-degree rotation. We're taking that figure, okay, and we are rotating it, basically flipping it, and it's going to be right back where it started. Okay, so notice that it says symmetry. It's got to be right back on top of itself. If I flip it 90 degrees, it's going to be sitting kind of up on edge. That's not going to be back on itself. So I'm going to have to flip it an entire clear, basically on the opposite side of itself, to end up landing back on the same spot that I was. Okay, this one here, you could do a lot of different things here. You could do it in 45-degree rotations. You could take that point and you could rotate this thing 45 degrees at a time. Okay, so you could do a 45-degree rotation. Anybody want to know, or how would I get 45 degrees here? Anybody want to take a guess on how I would get, where would 45 degrees come from? What would be a full rotation? 360, right? One, if I move this, if I just take this, turn it all the way around, it's 360, right? What were you going to say, Zandy? 360 divided by 8, because there's 8 sides. That's exactly right. So we could do it from vertice to vertice. I could take this and I could rotate it 45 degrees at a time, and I would still end up on itself. I could just keep rotating it, keep twisting it. So we would say that this could have a 45 degree, it could have a 90 degree, and we could list it all the way out. 180, 360, there's a bunch of different rotations that would be here, and you would still be the same figure, okay, right on top of itself. Okay, a figure like this, what do you guys think? If I went clear over here, could I do it? Nope. Okay. Do what? I could do a full 360, right? Everything can be rotated a full 360, okay? Can I do like a 180 or a 90? No, okay? If I did a 180, this figure is going to be landing over here, and it's going to be in a different location. It's different than the parallel there, okay? Even a full 90, this would come like right here. This would be short of over here, and so there are no rotational symmetries here. I can take that figure, I can rotate it, and see what it looks like, but it won't end up on top of itself. So that one does not have rotational symmetry. It's a little bit different kind of visual, and like I said, we're not going to spend a lot of time with rotations. More than anything, it's just something we want you to be exposed to and have seen and talk about, because we'll see some of those things later on, like the 360 divided by 8 and the 45 degrees and things like that. All right, so the big topic today, though, is 4-4. I didn't even put 4-3 up on the board, and we won't do a whole lot talking about 4-3. 4-4 is our big topic for the day. Two geometric figures are congruent figures if and only if, it's been a while since we've seen that statement, right? If and only if, we saw that way back in chapter 2 when we talked about biconditionals. If and only if there is a rigid motion or a composition of rigid motions, okay? Rigid motion is the only type of transformation that we have seen so far. Rigid motion means the triangle or rectangle or whatever I start with will be the same all the way through. No matter what kind of change I do to it, rigid motion means everything about it is the same. The side lengths are the same, the angle measures are the same. I have the exact same figure. It's just going to be in a little bit different spot. I slide it over, I rotate it, I reflect it. Those are all the ones that we've seen so far. All of those maintain the same figure. I get exactly the same figure back. So that's what we talked about. That could be one transformation, it could be multiple transformations. But if I have the exact same size and shape, then we have a congruent figure. So same size, same shape means the two figures are congruent. Very rarely are we ever going to change the shape, right? I'm not going to change a triangle into a rectangle. That would be a transformation, but it's a completely different transformation. When we talk about changing the size, that'll be later on in the chapter where we take a triangle and we blow it up to make a really big triangle, or we take a triangle and make it really small. That would be like a photograph. Like if I see a photograph, it's the same picture, right? If I take a picture and I want to blow it up and put it on the wall and make an 8x10 out of it, then I want that picture, I don't want it to be blurry or look different than what the actual picture is. So everything on that picture has to be enlarged. Or if I want to make like a little wallet size of it, that would be where we change the size of something. Okay, identify congruent figures in the coordinate plane, explain why. So we're going to look at figures on the one on the left. What two figures may be congruent? Name one pair. Okay, which ones? Who said that? Did you say one? Which two did you say? Okay, MKL and GEF. Okay, how do we know that those two are exactly the same size and shape? Looks like it, right? Okay. And so what we would want to say here is we would want to apply some type of transformation to it, okay? So if I looked at these two figures, they are congruent, okay? Then what transformation do you think is being applied to those two? Yeah, it's going to flip over the x-axis, okay? So we would say here that triangle GEF is congruent to triangle MKL. Because it's going to reflect over the x-axis. Okay. Another one that would be pretty easy to identify would be one like this. Okay, just look at the size and shape of this. What kind of figure do we have right here? What kind of geometric figure is this guy? It's a square. How do we know it's a square through here?
4 sides.
It has 4 sides. And what's special about those 4 sides? They're all the same. This one's 2 long, this one's 2, this one's 2, and this one's 2. It's 2 on every single side, right? And I look up here and I see this one is also a square, right? It's 2 on every single side. Now, I wouldn't want to do 3. I wouldn't want to do one that has 3 on each side because those 2 wouldn't be congruent. So it has to be the same length on each side. And so another one I could say here would be, it's not a triangle, but I would say ABCD is congruent to NPQR. Okay, one thing I will tell you here is you got to be careful of the letters and the order that you put them in, right? Because the easiest way to take this figure and move it down here would be to do what? What's the easiest transformation that we could apply to it?
Two down 6.
Yeah, we're just going to slide it, right? I'm just going to slide this right on top of this one. But A has to match here. So notice how I matched up A and N together. B has to match up with P. C matches with Q. D matches with R. Those points have to match up with one another because those are in the same spot with one another. If I said I'm going to go from D to R, it has to be the same as going from B to P all the way through, okay? And then that's what we talked about. So if I wanted to go from A to N, and you can use any of these, I'm going to go over 2, left 2, and then I'm going to go down 1, 2, 3, 4, 5, 6. And so we would say that this is a translation. And my translation rule here would be x minus 2, because it goes left 2, and y minus 6, because it goes down 6. Okay. So all of our transformations are basically in play here. I can do any of the ones that I want to do. We just have to identify why and how are we getting from one to the other. We did that a little bit yesterday, but we're doing it even more today. And what maintains the congruency? All right, on this one over here, I'm not going to write it out. I'm just going to mark or match up the ones that are congruent. So let's start with ABC. Is there another triangle that is the same as ABC? Okay, FDE. What kind of movement or change? Did we just slide it? Am I just taking this and sliding it over here? Yeah.
X plus 3 and y minus 2, and then a rotation of 90 degrees, right?
Okay. Yeah. And so I'm not necessarily going to, so you can, in your explanation, you would say we're going to move it and then we could rotate it. And especially for rotations, I'm not going to ask you to identify like how many degrees we're rotating because we're not going to spend a lot of time. But it is a rotation, right? We got to get B, A, B, and C to rotate over to match up with these. It is the same size, but we would just say that it's a rotation. Okay. What if I do this one here? What would IHJGJ match up with? Okay. Could it also match up with this guy down here? No, why not? Not equal, right? This one has 2 units, 2 boxes in it. These 2 only have, or this one has 3, sorry, these only have 2 boxes in it, right? So they are not the same size. So those two would not be the same. Okay, is WZYX going to match with anything? No, it's kind of its own figure. There's no other figure that looks like this one. Okay, and then finally, obviously, the last one, these could match up with one another. And that would just be a real basic reflection over the y-axis. Okay, another name for a rigid motion or a combination of rigid motions is what we call a congruence transformation. And all that means is we've done a transformation that has maintained congruence. Congruence means the two figures are going to be exactly the same. I'm going to transform them, but I'm not changing the size of the figure. I'm going to maintain the congruence of the two figures. All the sides are the same length. Everything about them will be the same one. Okay. So on this one here, if it just says to explain, you wouldn't necessarily have to get real specific with it. If I want you to describe, I would probably give you one that's a little bit easier to describe. How do I get from one to the other? Okay? So if I said, and this is kind of like what I was talking about on the quiz yesterday, we have to identify which one we're starting with and which one we're moving to. So we're going to start at A, B, C, D, and I want to move to E, F, G, H. Can I simply just slide this guy on top of the green figure? No, right? Because they're sitting different directions right now. And if they're sitting different directions, what am I going to have to do to get them to sit the right direction? Reflect it, okay? And so you can do this a couple of different ways. You can either slide it over or down first and then reflect it, or you can reflect it first and then move it down, okay? Yesterday on the glide reflection, and we had it listed out that way, you had to do the translation first, and then you had to do the reflection. Here, you could do it either way. You got a couple of options. Okay? So what I think would probably be the easiest here, just to keep it the same, is let's move it and get it ready to reflect. So this is going to become A prime. This is going to become D prime. This is going to become C prime. And this is going to become B prime. So my first movement here and if it doesn't say to write the rule, you could just say down 4 units, and I'm fine with that, okay? If it says to write the rule, that's where you'll use the X, Y, and you'll use all that terminology that we did yesterday on the quiz. But here I can just simply say 1, 2, 3, 4. We moved it down 4. Okay, now to get the red figure over to the green figure, what are we going to do? We fucked over the y-axis. Good. Okay, and all those points. D is 2 to the right, H is 2 to the left. C is going to go to G, B is going to go to F, A is going to go to E. All of those are going to reflect right on top of that. Now, what do you think would happen if I said, let's go from green to blue? Let's go the opposite direction. Let's start at the green figure and let's go to the blue figure. How much is going to be different? What would I do first if I wanted to go from green to blue? What would be one thing I could, there's several different ways you could go about this, but what would be one way I could do it? Yeah, okay. It's going to be just the opposite, right? I'm going to say up 4 units and then reflect the y-axis. So it's just the opposite of what the other one was. because we're still dealing with the same two figures. This one said down 4, reflect. This one I could do up 4 and reflect. I also could reflect it first and then go up 4. So the order doesn't necessarily matter in this case. It would get me to the same place. Okay, try this one. See if you can figure out the transformation that would map KLJ to NPM. Go blue to green. See if you can figure out the transformation. I'll give you a couple minutes. And if you need to draw a new figure in between to show where it would be, that's okay too. You wouldn't necessarily have to do that, but you could. I'll also say there's more than one right answer on this. Okay, there's more than one way you could do it. That's not for you guys to worry about. That's for me to make it harder for me to grade, because there's more than one way you could do it. All right, going blue to red. Anybody want to tell me what would be one way to do it? Berkeley? No? Hendricks? Did you do it? No? Bryson?
Heck no, I didn't do it.
Why not?
I don't even know how to do it.
You don't know how to do it?
Well, I'm listening.
Huh? So, okay, so let's just do this. Let's talk about it. What can I just slide blue right on top of green? No. So what are we going to have to do probably first? Any ideas? Nothing, Bryson?
No.
None of the transformations we've talked about so far? Okay, yeah. So there's two options here, right? I could either move it over here or I could move it over here, okay? Well, and let's say I move it over 4, right 4, okay? Or however many units I have to move it. I need to match up this point right here so that it's ready to reflect. Because right now this point is 2 above and this one is 2 below, right? So I gotta move L over to this spot right here. So I gotta go 1, 2, 3, 4, 5. I gotta move it right 5. But if I do that, I gotta do all of them. So J, I'm gonna move it 1, 2, 3, 4, 5. And then K is 1, 2, 3, 4, 5. We moved it right 5. Okay, and then once I have it set up, now look at all my points. 2 above, 2 below. This one here is 1, 2, 3, 4 to the x-axis. I can go 1, 2, 3, 4 on the opposite side of the x-axis. So we're just reflecting it over the x-axis. If the figure is sitting a different direction, what are we going to have to do? We're going to have to reflect it at some point in time, right? Did anybody reflect it first to come down here? No. Could I have done that? Could I have reflected the blue guy down here and then slid it over? Yeah, it would work the same way, right? The second one says, what if I want to go from green back to blue? What if I wanted to start down here at NPM and I want to get up to blue? Guess what we're going to do? We're going to do just the opposite of what we did here, okay? So I'm going to go from green back to red, which means I'm going to reflect the x-axis. So I'm just going the opposite direction. Now, what would I do to move from the red one back to the blue one? Left 5, okay? We got to go the opposite of what we did to start with. So I could go either direction. Will you have to do both of those? Not necessarily, but we're just showing you that as I move it, I can go from one to the other, and it doesn't matter which one I start with. Neither one of them is necessarily the original or the prime notation, because we're not using prime notation really today. It's not A and A prime or B and B prime. It's two completely different figures, okay? And so we don't know if they have any congruence. But are these the same size? Yeah, because when I map it on top of itself, it gets me the exact same figure that I started with. Okay, this one's a little bit harder because they're not graphed for us, okay? And I will tell you, there was a little bit of issue yesterday in graphing points, okay? So you got to really be careful, positives and negatives especially. If it was 3, 2, sometimes people went over 3 and down 2 instead of over 3 and up 2. I had a lot of, that was probably one of the biggest mistakes that was made over and over again. If we don't plot the figure in the right spot, I'm not going to get the correct figure. So we got to be really careful about our points. So we're going to start with 0, 0, 1, 2, 4, 2, 3, 0. There's A, B, C, D. Okay. E, F, G, H is at 0, negative 5. Negative 1, negative 3. Negative 4, negative 3. Negative 3, negative 5. Okay, one thing that I would tell you to pay attention to here especially is A is going to map to E, right? Because those are the first two letters that are listed out here. And we know, just by looking at this, I can't slide the blue right on top of the red. They're sitting different directions, right? So immediately that tells me I know I have to do what? If the two figures are sitting in a different direction, I got to do what? I got to reflect it, okay? What would be the best place to reflect this over the y-axis, right? If I reflect it over the y-axis, A is going to stay where it's at, B is going to come here, C is going to be here, and then D is here. Okay, now, are those two figures sitting in the same direction? Yeah, okay, so my first thing was we reflected the y-axis, and now I got to take the black figure and put it on top of the red figure. So now I got to figure out what do I have to do to get there? So if I wanted to get from A to E, do I have to move it left or right at all? No. How far do I have to move to get from A to E? Down 5. We only had 4 days this week. You guys are like dead tired today, man. Guess we'll have to stop giving you a day off during the week, right? 5 days every week. Okay, so I could have done it another way, right? I could have reflected it first and then moved it. There's other ways to do this, but that would be one way to get there.
Mr.
Yeah.
Do